Last but not least, Troy Gilmore. He's a groundwater hydrologist and assistant professor with the University of Nebraska. And Troy is going to talk about estimating water quality lag times using groundwater age. And it looks like your video is, it was up. There we go. And with that, Troy, you can take it away. You are on mute though. We still got you on mute, Troy.
Sorry about that. I can only do one thing at a time, I guess. Now you have audio and visual?
We got both.
All right, great. All right, so thank you everyone for hanging on till the end of the day, and I appreciate the organizers for inviting me to talk a little bit about water quality time lags and groundwater age. And the other folks who spoke have set things up very nicely. I was actually just on, I was doing some Googling and was just on that South Dakota water quality website and was really impressed with it. There's some similar efforts going on to develop that type of thing in Nebraska, and we know that it is non-trivial, and appreciate that, what you're doing. So I'm just going to get started with a simple definition, which suggests that my talk should be really simple. We're just talking about a period of time between one event and another. But for those of us who dreaded the train problems in algebra or physics, you know that just getting two events lined up in time is a bit more complicated. And when we're talking about water quality, whether surface water, groundwater, or both, we're probably dealing with something that's more like this, really complicated situation with different motivations, different drivers, different timetables, all of that coming together as a really complicated picture. And in terms of time lags, I'm going to present today just kind of a little snippet of this complicated picture, talking about groundwater, a little bit of surface water, but my idea is to share why we're interested in groundwater lag times for both groundwater and surface water, how we use groundwater age to reconstruct contaminant history to some degree. And then I'm going to give 3 examples of studies where we've used groundwater age to not only reconstruct, but in some cases we can use the groundwater age information and the lag time information to actually predict, look forward to when we might have water quality improvements that result from water quality initiatives. So this is an imperfect analogy, but you might look at this rail yard and now segue into the generic watershed that I've sketched down here below, where you have a lot of different factors that other speakers today have already mentioned, influencing what is actually getting funneled out at the downstream end of these systems. And just a few of those factors include things we've heard about: contaminant sources and loading, hydrology, biogeochemistry, the monitoring programs that we have, and what those are designed for in telling us about the system, and then the regulation and management that might result from that. And all of these factors have some kind of time component, some temporal aspect, and some example questions I've put on here, such as how the loading might change over time, how quickly are contaminants moving into and through the system. It's a fundamental part of the lag time question. Chemical reaction rates, maybe you have denitrification in an aquifer that's removing nitrate, for instance, but that depends a little bit on residence time. How is monitoring, maybe priorities have changed, maybe funding has changed like we just heard about, and then how is that information used and when is it used to enact regulation or maybe management practices being adopted. So there's this time component kind of threaded all through this water quality picture, at least for someone like myself who's interested in time lags. That's what I see. So some of you on this call may have experienced this. What's being described in this quote, you can have some disillusionment, particularly if water quality initiatives do not account for, in some cases, the type of lag times that might be associated with the time between, say, nutrient and water management, changes in that, in nutrient water management, the time between that and when the positive effects are achieved. And especially with groundwater, we can get into some pretty long lag times. And so when you're thinking about this watershed that's sketched here, and then you start thinking about the groundwater that lies beneath it, we're talking about, in many cases, kind of delayed gratification in terms of seeing the kinds of benefits of our water quality initiatives that we want to see. So I'm just going to slice in just this hypothetical watershed along that red line that I'm showing there, and use this figure from Tesserero et al. 2013 as a nice overview of a unconfined aquifer in an agricultural area. And it just illustrates how, it reminds us that surface water quality can be affected by groundwater quality. Of course, you have these other quicker flow paths like tile drainage and overland flow here as well. But this figure is highlighting, just like we heard about in the last talk, where young groundwater, for instance, near the water table, maybe that's high in nitrate discharging to a stream, while you may have at the same time older groundwater from deeper in the aquifer discharging to the stream also. And so that mixture could potentially affect surface water quality. So one question when we start talking about groundwater surface water interaction like this is, where is it relevant? And this map is from that same paper written by USGS scientists, but it's available in the Environmental Science and Technology Journal. You can see from this that they've highlighted areas with a base flow index of greater than 0.4. So 40% of the annual stream flow is attributed to base flow in these shaded areas. Much of that is going to come from groundwater in a lot of the cases. And then the darker shaded areas are showing you where you have a lot of nitrogen inputs. In terms of eastern and northeastern South Dakota, which is probably where most of you are looking on that map right now, you see that that area is not even shaded, whereas down in Nebraska, where I'm at, we have a lot of these areas that are shaded. There might be, and I do not know the geology of South Dakota, but there are others on this call that could probably comment on if there's some potential for local areas of connectivity between groundwater and surface water, but it looks like there might be some of that potential in the southwestern areas. So in addition to that issue of groundwater potentially affecting surface water, we're also very concerned or interested in the groundwater nitrate in the aquifer itself. So in Nebraska, we have about 85–90% of the people are relying on groundwater for their drinking water supply. And so that map on the right is really important in terms of a lot of domestic wells out in these areas where there are high nitrate concentrations. And you can see there the purple areas reaching up into the 200 to 100 milligrams N per liter in these areas. So we do have some high nitrate concentrations. It's also been heavily monitored for a long time. So we have a lot of data behind this map. So both groundwater and streams have this potential of being affected by nitrate, and in the context of this talk, also being affected by the lag times that we see in groundwater. So because the groundwater moves slowly, it is in some senses a bit of an archive, water quality archive. So we can go in and look at, for instance, in an unconfined aquifer like this, as I mentioned earlier, you might see that young groundwater close to the water table having a higher contaminant concentration like nitrate, and the older groundwater that's further away from the recharge area, further away from the point where it originally recharged, may even predate some human activity like the widespread use of commercial fertilizer. But a lot of agricultural watersheds, groundwater recharge since the 1950s is often higher in nitrate. One of the caveats, you may have noticed that I referred to the point of recharge when I talked about the older groundwater age. And that's because for the most part, when you read or hear about groundwater age, there is a reference. The reference point for that is the time of recharge. So for the most part, you hear groundwater age, it's ignoring the beta zone transport. And the reason for that is that most age dating tracers that we use are dissolved gases, and those tend to be equilibrated in the beta zone. But once the water is recharged and below the water table, then those dissolved gases are kind of locked in to the groundwater, and then we can measure them later and determine the groundwater age, but it's relative to the time of recharge. So how can we access this information? A very classic way of doing this, and there are other ways, but a very classic or nice way of doing this is to use multi-level wells. So your groundwater monitoring network in South Dakota is set up nicely for this, at least having a shallow and a deep well. But you combine that access to the groundwater at multiple levels in the aquifer with groundwater age dating and water quality analysis. So here's an example, just hypothetical, of, let's say that you sampled these 3 wells. They're co-located, but they're at 3 different depths and they have pretty short screens. So when I looked at at the South Dakota water quality website, I saw screen lengths, I think they were about 5 to 10 foot, a lot of those screen lengths. And those would probably be reasonable for this type of work. We have installed wells with screens as short as 1 foot for this type of purpose, for this type of sampling, just to try to constrain to get more discrete information from different depths. At any rate, once we've collected this groundwater, we've analyzed it, and we come up with a groundwater age based on, say, chlorofluorocarbons, CFCs, or tritium helium age dating. We often plot that up as a function of depth below the water table. And then on the horizontal axis, you see the term apparent age. We like to say apparent age because we're using imperfect tracers and we're acknowledging that these are estimates. These are tracer-based estimates, they're imperfect. And they're usually not going to fit that model line quite as well as I've made in this hypothetical example. But the point with the line, the model fit there, is that we do have some very simple models, especially for an unconfined aquifer like this, where we can fit the model to the age versus depth plot like this, and we can actually from that determine a recharge rate, which is the slope of that line at the water table. So we can get flux information from these different ages at depth in an unconfined aquifer. We like to combine with that, like I said, some water quality information. Here's another hypothetical of some different nitrate concentrations from those same wells. And with both of those pieces of information, here's the plot that we're really going after to reconstruct some history of nitrate inputs. Now, this is assuming either there's no denitrification, that's removed nitrate in this case, or that we've also measured N2 gas in these samples, and we've been able to reconstruct how much nitrate had been removed by denitrification and then adjusted these values for that. But the general idea is that you now have a nitrate concentration versus recharge year plot. And these recharge years are just calculated by taking the sampling year minus the apparent age. So I pretended that these samples were collected in 2020. Assuming you've been able to account for denitrification, maybe you start to think, wow, this could be some improvement here in more recent years. More recently recharged groundwater has lower nitrate, but you probably don't want to do that just on a single well nest or just 3 samples like this, but you start to maybe get some hints that way through this reconstruction effort. So now we're going to shift to some real examples, and I'm going to give you 3 real examples. This first one is really nice. It's USGS data published in also in ES&T. They sampled a lot of groundwater in a lot of different agricultural watersheds across the US. Keep in mind that the next plot that I show you is the result of a very short period of monitoring or sampling. So we're not talking about decades-long monitoring. We're talking about a few years maybe of sampling that happened, then a bunch of age dating analyses, and then they're able to construct this plot. So what they've done is gone through that same scenario I described earlier, calculating a groundwater age, and then you can plot the sample or the nitrate concentration by the recharge year as shown here. And so you're seeing kind of this long history of nitrate entering aquifers across the US. This is also adjusted for denitrification. They've accounted for that. But you see background concentrations back in 1940s. And based on that red line fit there, kind of a smooth curve up to about 15 parts per million in 2003. So this is a big, broad study by USGS. I'll share another example of a more intensive type of sampling that was done in a small watershed in eastern North Carolina. In this study, in the upper right-hand map, you can see the 2 green stars. Each of those stars represents a 3-well nest, like I depicted earlier. So we sampled well nests here. And then we also went into the stream itself. This is a gaining stream, and we used handheld piezometers, which we pushed into the stream. And we were collecting groundwater from about 2 to 3 inch screens that are pushed about a foot deep into this stream bed. But we were actually collecting groundwater just below the stream bed right before it emerged into the stream. So we were able to make similar plots to what we just saw from that larger USGS study. So on the vertical axis, we have initial nitrate concentration. That's the same as a recharge nitrate concentration. These are also corrected for denitrification. And we sampled groundwater at 2 different spatial scales, a 60 meter and 2.5 kilometer reaches. And then I'm showing also here the results from those 2 well nests that we had. But in our analysis, we felt like we were seeing from several different lines of evidence, but shown in this plot, we're seeing perhaps a peak in nitrate inputs to the aquifer in the mid-90s, and then perhaps some improvement in more recent years. And so that's why we're showing these 2 different regression lines with admittedly pretty low R-squared on some of these. But like I said, it was a complicated, or it was a more involved study than just those 3 plots. When we combine that nitrate concentration plus the recharge year information with groundwater flux information, that is flux, that's groundwater discharge to the stream or groundwater recharge to the aquifer. When we bring in some additional information and use some very simple models, like I mentioned earlier, we can actually get into move from a reconstruction or reconstructing the past mode into more of a predictive mode. And that's what this second figure on the right is, where we were looking at several different scenarios and trying to predict the nitrate concentration of groundwater that is discharging from this aquifer in the future. And the short takeaway from this is that if you look particularly at the open circles on the upper two plots, those are imagining that nitrate concentrations in recharge we're going to continue to decrease all the way down to 0. But if you look down at the bottom axis, you can see that we're talking easily 15, 20 years before we see any significant reduction in nitrate concentration in aquifer discharge here. And that's a major piece of information if you're looking at trying to improve stream water quality in this location. This stream had about 50% or a base flow index of 0.5. So about 50% of the water in that annual discharge was from groundwater. So you're going to have to find other ways to reduce nitrate loading to the stream if you want to do that in a short period of time. So this last example is we're going to take you out to the far western edge of Nebraska in the Dutch Flats study area. This is in the North Platte Natural Resource District area. You can see all these black dots on this map are, almost all of those are well nests, or the majority of them. So this is a very, very intensively monitored area in terms of nitrate. You can see some canals there that are feeding irrigation. This is what the landscape looks like. A lot of surface irrigation in the past, big shift to center pivot more recently. But what we wanted to do in this study, one of the things was to use groundwater age dating to inform our modeling. So we're kind of using the age dating in a little more indirect way than in the previous examples that I showed you. So this plot shows about 1,000 nitrate observations from that small study area. They are coming from well nests. And this is just a subset of the available information, actually. We selected this based on the way that it was monitored during that time period. But what we did was we took some groundwater age information from previous studies and we added to that with a few more, we sampled a few more wells ourselves. We calculated recharge rates based on those groundwater ages that were observed to give us some constraints on vertical transport rates for nitrate, both in the vadozone, because if you know a recharge rate, you have to have vadozone water feeding, right, to create that recharge, and transport in the aquifer or in the groundwater itself. So we use that to constrain a likely range of transport rates, which we then fed into machine learning models to build and test machine learning models. And from that, we selected what we thought was the best performing model, and therefore we had what we considered our optimal transport rates. So we're combining a little bit of age information with a lot of monitoring, nitrate monitoring information to build and test machine learning models to come up with some transport rates for groundwater and for nitrate in that area. And so when it's all said and done, we can take this top plot, which is the original observations, based on the transport rates that we determined in our modeling. We can show those same exact observations, but shifted in time to represent about the time that we think that nitrate was in water that was infiltrating at the land surface. So we've been able to take a little bit of age information and really hopefully inform ourselves a little bit about how this and when this nitrate entered the system. That's a messy plot, obviously, but it has some of the same characteristics that we saw in that first plot of kind of that nationwide view of nitrate in agricultural watersheds. And then for the final slide in terms of these example studies, one of the nice things about the machine learning, this particular random forest regression model, is that you can see for every variable that you use in the model, you can see the response variable versus that predictor variable. We can see plots of those, the relationship that was built by the model. And here what we're seeing is, there are a lot of wells in that area that total travel time, Betos and ground and saturated zone travel times are less than 7 years. So this is really important information, suggesting that a lot of these, if there were major changes in nutrient and water management in the area, that there could be a pretty rapid, in terms of groundwater, response to that in this area. So this is the kind of information that we're trying to draw out when we're studying lag times in these kinds of systems. So just to conclude, our water quality solutions may not be as timely as we imagine. Estimating lag times can help establish realistic timescales. We can not only look back, but we can start looking forward a little bit as well when we have this information. And with that, I again thank you everyone for your attention, and want to thank the conveners as well, and invite you, there's a short URL here you can write down if you want to check out more information on this type of work.
Okay, thank you, Troy. Any questions for Troy before we wrap things up here?
I have one, Troy. So obviously the situation in South Dakota is different than Nebraska in terms of spatial density of wells and things like that. But how do you think that groundwater age dating could be used to help inform? Do you think it could be used to help inform some of the analysis that's being done by South Dakota Geological Survey for their wells?
As a proponent of age dating, yes. But in all seriousness, I think there's one of the things I noticed was there were a lot of, well, I shouldn't say this. It seemed like there were a number of wells where you have high nitrate in the shallow one, and the deeper well is just practically zero. And I thought that was an interesting feature that could be looked at. Is that what exactly is driving that? Just in general, one of the things that I've mentioned to management districts in Nebraska is you might be able to, if you know the age of groundwater coming into a particular well, if it's extremely old, you might be able to reduce your sampling frequency on that, for instance, just because of the low probability of seeing nitrate anytime in the near future.
Okay, we've got a couple more questions here. Jay asks, have there been instances where you have been able to verify predicted lag times over a long period of study?
That's a good question. I have not personally in my work pulled that off. I'm trying to think of other scenarios. One of the things I did not get into at all here was that, for instance, municipal wells, which have very long screens, they're drawing in a real mixture of they're potentially drawing in a mixture of shallow, high nitrate groundwater and deeper, low nitrate groundwater. And I think there have been cases where they're able to kind of tease that out and adjust things in how do I say this exactly? Basically, by adjusting that young fraction that they're pulling into that well, they're able to resolve their nitrate issues, for example. And so that's a kind of a verification of that what they're seeing there is real. But as far as taking, I haven't done that myself, I guess, is my shorter answer.
Okay, thank you, Troy.
Thank you all very much.
And with that, I think we're going to wrap up. We hit her pretty close to 2 o'clock, so I'm pretty pleased with that. So we didn't want to keep you guys here all day. So I want to thank our presenters for their interesting talks, and I especially want to thank all of our participants and attendees for trying this. You know, we've had this up on campus for many years, and this is our first virtual conference. And you know, some of you've got some comments on it. You know how to contact John and I and give us your thoughts on how you felt about this virtual conference. So, John, do you have anything to say before we wrap up here?
I'm not really, but I guess just to re-echo my opening comments. Again, we covered a range of things. Some are more informational, some are actionable. And so if there are ways that you see you can take action, then yeah, use this as an opportunity and a springboard. And yes, please, we will send out, or I guess we request feedback on the format, speakers, things like that. And you know, our preference is to have it in person, but there are a lot of advantages to having something virtual. And so let us know what you think, and even the possibility of doing some type of hybrid next year. So
yeah.
Thanks.
And again, these presentations have been recorded and they will go up on the website. We'll do a mass email for everybody that attended to let you know when that happened. Those will go up on the conference website, so you can peruse them as you like.
And I guess one other thing is big thanks to Lindsay Gerard and her team with SDSU Extension technology folks for the behind the scenes stuff and making all the technology work.
Absolutely. If this was left up to me, the conference would not have happened because I'm not very good with technology. So with that, I think we'll call her a day. And thank you, everyone.